Well, you gotta keep the dust out of it.
How fast do you type?
Alright, what's the time? Yeah.
Average time.
So, I think today we're just gonna go over the practice exam because you have your exam on Thursday. And we'll probably end early unless people have lots of questions, so feel free to ask questions. You don't have to, but feel free. So this is the review sheet that is in D2L in the exam review folder? I forgot what it's called, but it's the same one as last time. You don't have to bring a Scantron. I have a few extra. Next term though, since there's going to be a lot more classes on campus, you'll have to bring your own. You buy them at the student store. I think they come in packs of 5. So don't worry about it this year. This term. Next term though. So I want to make sure everybody knows the stuff that we're going to cover. So 7B, that is the energy level calculations, going from change in energy to photon wavelength, things like that. And then everything to do with the shell model, including photoelectron spectroscopy, all the periodic trends, including size, ionization energy, and then linking all that to the quantum mechanical atom. So honestly, the stuff from the quantum mechanical atom is just going to be the interesting concepts like Heisenberg's uncertainty principle, what that does for us, and then how we link the quantum numbers to the shell model we know. So energy levels is N, shell, subshell is L, things like that. And then electron configuration, it all kind of goes together with that. So this is it, but chemistry is cumulative by nature, so make sure you can use Coulomb's law to explain some of these things where it's necessary. Significant figures are always a good thing to keep up with. And then don't forget to review the homework.
Oh, can you go back for just a quick second? Okay, you're good. I got it. I just missed the word.
Okay. So anyway, this is on D2L. You can see it there too. And all the topics are broken down very, very finely here. So make sure you take a look at this stuff. It's all in there. Some of the stuff from the lab is important. So there's not going to be any specific questions from the lab, but you know, the concepts you learned. So Tyndall effect, with this laser scattering, concentration calculations that we did. So all that is valid. All right. So we're just going to go straight into the practice exam. So you'll get in the exam on Thursday something like this, not in color, but at least labeled out like this with the blue, green, yellow indicators. So this was on the last exam, so it's no big surprise. We got this. I think Coulomb's law is missing from this, but if you'll need it, that'll be in there too. The Bohr/Rydberg equation here, which is for calculating the energy levels. Here is the Coulomb's law K value for plugging in picometers for your distance and getting joules out. And then we've got the speed of light, all that stuff. Energy of a photon, and so forth. Okay, no big surprise. So let's go straight to the questions. And again, interrupt me if you need, ask questions, whatever you need.
I'm sorry, really?
Yeah.
Is the answers posted on D2L too?
They should be. They are, okay.
There.
Good. Okay, so which transition in the spectrum of hydrogen results in the emission of light with the longest wavelength? So a key thing to watch out for when you see these is knowing if it's an emission of light or an absorption of light. So an emission of light only occurs when your transition is from a high energy level to a lower level. So you can throw out D and E here because you're going from low to high. In order for that to happen, the atom has to absorb energy, absorbing a photon. So we're emitting a photon. So it's one of these. And this is where you kind of just have to know, in general, what the energy levels look like. Not necessarily where they are exactly, but what kind of pattern they make. And you start off with 1 at the bottom, then 2, and there's a big gap. And then 3, and the gaps start getting smaller and smaller and smaller. That's the relative pattern that you're going to see. So, if we want a long wavelength means low energy, right? They're inversely proportional. So we want the smallest energy photon. So we want the smallest transition. So 3 to 2 is right here. That's pretty big. 3 to 1 is even bigger. But a 5 to 4 looks pretty tiny to me. So this transition listed, number C, is going to give us the smallest energy photon, which means the longest wavelength. So, C. Okay. Honestly, I think this is like the most, not complicated, but the most detailed question here. Which of the following transitions results in the absorption of photon with the largest energy? So this is the other way. We want the largest energy, so we're pretty nice and simple here. You can draw them out if you want, but 7 to 1, that's an emission. 3 to 1, that's an emission. You can rule this out. These are absorptions. They're low to high. And the biggest transition is probably the 1 to 4. So going from 1 all the way to 4 gives you the largest change in energy for an atom. And so you're going to have a large energy photon hitting that atom in order for that to happen. So again, C. Okay. What is the energy of light emitted when an electron falls from n is equal to 4 to n is equal to 2? Okay, so if we focus on just that one transition, you can almost memorize this. I think you guys have calculated this several times in different ways. So we're going from 4 to 2, and we actually have to calculate an energy. So this is where we use the Bohr equation. So if you go back to this thing, we're looking at this equation right here. And we are calculating the energies difference between energy level 4 and energy level 2, which each have their own potential energies. So we need to calculate those potential energies first, and then we're going to take the difference between them. So energy level 4 is minus 2.178 times 10 to the minus 18. Z is always based on what kind of atom we're dealing with. So just to make sure, we go back, this is for the hydrogen atom. So Z is 1. And then N is our energy level. We're doing 4. 4 squared is 16. So this is going to give us, and I forgot to get my calculator. Negative 2.178 e to the minus 18 divided by 16. Negative 1.36. 1 times 10 to the minus 19 joules. Energy level 2 is the same calculation, except we're going to plug in a 2 for energy level 2. So 4 instead. Negative 5.445 times 10 to the minus 19. Now we do the change in energy for the atom. Alright, change in energy is always final minus initial. So the final state is energy level 2. So we plug in that here. 4 times 10 to the minus 19 minus the initial state, which is energy level 4, a negative 1.361 times 10 to the minus 19. So make sure you plug this in your calculator correctly. It's actually not a big deal, but the minus a negative 1.361 e to the minus 19. And I get a negative 4.084 times 10 to the minus 19. The negative here for a change in energy means the atom has lost energy. So for any change in energy, a negative means loss. Positive means gain. So that makes sense. The atom is losing energy. Where does that energy go? It goes out as a photon. So the photon has positive 4.08 or 4.09 A times 10 to the minus 19 joules of energy.
So could you explain again how it, in words, how you got it to be positive?
So
you said it
so
lost
that
energy.
so the change in energy, this delta E, is for the atom itself. The atom is losing energy, and you can see it because your electron is going from a high energy state to a low energy state. So if the atom has lost that energy, according to the law of conservation of energy, you can't destroy energy, so where did the energy go? It's been emitted as a photon. A photon is a packet of energy. That's how the energy is lost. So the photon has that 4.08 times 10 to the minus 18 joules of energy. It is energy. That's how you think of a photon. It's a little packet of energy.
So that's what we're talking about. We want to know how much energy the photon has after the transition.
Yes. Yes. Okay. All right, which atom is represented by the shell model with 2 electrons in the first shell, 5 electrons in the second shell? So there's a couple ways to do this. You can just add up all the electrons. 2 and 5 is 7. The atom with 7 electrons is nitrogen. Or you could just go by the shells. 2 in the first, 1, 2, that's hydrogen, helium, and then 5 in the second, 1, 2, 3, 4, 5 in the second row. That's still nitrogen. So I don't think this is a very super hard question, but it's nitrogen. All right, arrange in order of increasing first ionization energy. So sulfur, argon, and calcium. Sulfur is number 16, argon is number 18, and calcium is number 20. And it's in the next row. So you have to kind of do it one step at a time. So if we look at different rows, the calcium is going to have electrons in a 4th shell. We're doing ionization energy. And so anything in a 4th shell versus the 3rd shell, usually something in a 4th shell is going to be lower ionization energy. Usually, not always. But the other thing calcium's got going for it is it's further to the left. Elements that are further to the left have a lower ionization energy as well. So it's furthest to the left and it's furthest down on the periodic table. So calcium is going to have our lowest ionization energy. So between C and E, well, now we compare argon and sulfur. So those are easy to compare because they're in the same row. Yeah, question?
I was just gonna ask, obviously, like, from doing a shell model and thinking about it, you can see how many valence electrons, but I know you said, like, based off of something in the periodic table, would you just know how many? Can you tell us, like, how again?
Know how many?
How to, like, to know how many valence electrons there are without, like, thinking about the shell model? Right, just
It's just the group number they're in. So for calcium, it's in group 2, so it's got 2 valence electrons. That only works with the main group elements. It doesn't work with transition metals. Yeah.
Yeah, so gallium has 1 or 3 valence electrons. That was a question I think on my web board. But
yes, it should have 3 valence electrons.
but it's got the D orbital.
Yeah.
Those are just full
But
in the 3rd
so
shell.
if you look at the electron configuration, it's 4s2, 3d10, 4p1. So for main group elements, that 3d is full and it's in a lower shell.
Okay.
So we kind of ignore it. It's not really a valence electron.
Okay.
For transition metals, it's a unique situation because even though 3d and 4s are different shells, they're actually a lot closer in energy than main group elements, 4s and 3ds. And so you can consider the 3d as a transition, as a valence shell in this case. I'd have to show you like actual like energy level diagrams for the different elements, just to show you. When you get to the main group elements, suddenly the 3D is a little bit lower, and it's kind of off the grid now, and it's not really a valence shell anymore.
Oh, okay.
I think there's gray areas too. There's,
Yeah.
this is not an exact rule in this, but it works pretty well. Let's put it that way.
Okay.
So going back between argon and sulfur, as you go to the right, ionization energy increases. Argon should have the highest ionization energy, so it's E. Calcium is lowest. And that should make sense because calcium is a metal. Metals lose electrons, they become cations pretty easily. Nonmetals do not. So calcium is going to have the lowest ionization energy, then sulfur, then argon. Argon is a noble gas. That's going to be the one the most difficult to remove electrons from, generally. And when I give you these comparisons, these ranking, it should be fairly clear which one is higher and which one's lower. You're never going to get selenium versus chlorine, for instance, right? That's a little harder to kind of, which one's higher, because chlorine is further to the right, so it should be, oh, well, actually, no, other way around. Bromine and sulfur. So bromine's further to the right, so that should be higher ionization energy, but sulfur is higher shell, or lower shell, excuse me. So I won't give you that kind of comparison. I'll give you fair ones that you can really tell, okay? All right, number 6. This is a very specific problem. We've done a couple of these. Hopefully this isn't a big deal. We're looking at ionization energies, subsequent ionization energies for a single atom. So when you remove the first electron, it costs this much energy. The second electron costs this much. And you can see it keeps going up. And that makes sense because you're removing electrons, but you have the same number of protons. So you have less electron-electron repulsion. The remaining electrons are held on a little more tightly. So the ionization energy goes up. But then all of a sudden here, and it doesn't have to be the last one, but this particular change is a much, much bigger change than before. Here it's like doubling or not even doubling, but here it's quadrupling. And so what this is telling me is this 6th electron was not a valence electron, it was an inner electron. This is telling me that there are only 5 valence electrons, and so this has to be phosphorus if it's from period 3. So it's 5 valence electrons, has to be phosphorus. Core charge for silicon. You can calculate it, but we have an easy way to do this for neutral atoms. The core charge is the same as the valence electrons. Silicon is group 4, so 4 valence electrons and plus 4 core charge. All right, so neutral atoms are easier ones to do. Okay. Which atom requires largest amount of energy to remove the most tightly held electron? And the hint is it's the electron closest to the nucleus. So this is a little bit weird. We're not removing a valence electron. We can't use the periodic trends because that only works for valence, the first ionization energy, which is not what this is. This is removing an electron from the inner shell, the closest to the nucleus. So if you think about it, whatever atom that is, this electron on the closest to the nucleus is not being shielded by anything else. No shielding. So there's no core to worry about. There's no, maybe it's not feeling the entire nuclear charge. So really the one that's going to be hardest to remove is the one with the largest number of protons at the nucleus. The more protons there are, the harder it is going to be to remove whatever this inner electron is. So among the atoms listed there, looks like arsenic, As, is got the highest atomic number, the most protons. Number 33. So that is the one that is going to have the most tightly held electron at the inner shell. So it's going to take the most energy to remove that inner electron from arsenic. So ultimately, what does this mean? If you looked at a photoelectron spectrum and you had all the peaks from all the electrons, the furthest one to the left for arsenic would be the highest energy one out of all of the other photoelectron spectrums. which of the following groups of atoms does each atom have the same number of valence electrons? So you're really just looking for atoms that are in the same group of the periodic table, same column. And the only one that works is C. Carbon, silicon, germanium. They're in group 4, all of them. So these have the same number of valence electrons. In 222, we're going to dive right into studying this group in particular. It's a very interesting group. We make a lot of semiconductors using group 4. And if it's not group 4, we make other materials that are analogous to group 4. So gallium arsenide semiconductors. It's a mixture of group 3 and group 5, which look like group 4. Anyway, don't worry about that. That's 222 stuff. If you take chem next term, you'll see it. All right, so here is the promised concentration problems. You need to determine the molarity of a solution dissolved by forming 97.7 grams of lithium bromide in enough water to yield 3/4 of a liter of solution. So you need to know the concentration in molarity is achieved by doing moles of solute over liters of solution. So that's kind of the formula, if you want to do it by formula, how we're going to put this together. So our solute is the stuff we're dissolving. That's the lithium bromide. Well, that's in grams. So first things first, we need to convert this to moles. And we can do that using a molar mass. So lithium is 6.941. Bromine is 79.904. Yeah. And I get 86.845 grams for every 1 mole of this substance. So when I knock this out, 97.7 divided by the molar mass, 1.125 moles of lithium bromide. So now I've got my solute, 1.125, and I'm going to divide it by the volume of the solution in liters, so 750 milliliters. I'm going to take a shortcut here. You divide by 1,000, and you get 0.7500 liters. So I get 1.50 molar solution. 3 sig figs from here, so 3 sig figs in the end. So there's my concentration. We'll do the same thing, but backwards. So now, if I want to make a 3 molar solution, and this is what you guys did in the lab, and how much do I want to make? I want to make 1/4 liter, 250 milliliters. What mass of sodium chloride would I need to make this solution? So, another thing that I try to make everybody remember to do in their heads or on paper, as soon as you see molarity, this big M, translate that into what the unit means. So molar means moles per liter. That's what that means. So that's a conversion factor. It converts between liters and moles and liters. Well, I've got a volume, 250 milliliters. In liters, that's 0.2500 liters. If I multiply these, my liters cancel. And actually, I'm not going to add more. I get moles of solute when I do that. But I don't want moles, I want grams. And this is where molar mass comes in. I want to get rid of moles and have grams instead. So molar mass of sodium chloride, that's the solute. 2.98977 plus 35.4527, that's a lot of sig figs. 55.8, sorry, not 50, 58, excuse me. 58.44247, way more than necessary. So do the math, 0.25 times 3 times that molar mass, and you get 43.83 grams. 4 sig figs because everything's 4 sig figs.
Was that 58.442 or 0?
442.
Right, talking about needing glasses.
It's a curse, okay.
Right.
Yeah.
I was like, what am I looking at? I'm so confused.
Okay. So that's D. Here we go. All right. That's honestly basically it for solution stuff. It's not much we can do besides making solutions. That's it. So which of the following atoms has the largest size? So this is periodic trends. Sodium, potassium, calcium, magnesium, these are all kind of tightly grouped together. We know that as you go down a group, down the periodic table, they get bigger. So I'm going to ignore sodium and magnesium because potassium is bigger than sodium, calcium is bigger than magnesium. So between calcium and potassium, K and Ca, as you go left to right, things get smaller. So potassium is the biggest. Nope. Come on. There we go. Okay. So sulfide is isoelectronic with which noble gas? So make sure you know this nomenclature. All right. Sulfur is just S. That's sulfur. Sulfide is S2 minus. So we're talking about the ion here. Sulfide. So isoelectronic means same number of electrons. So this is sulfur with 2 extra electrons. Sulfur with 2 extra electrons looks just like argon. All right, sulfur's got 16, 2 extra is 18. That's argon. All right, which 2 atoms do not form isoelectronic ions? So again, same number of electrons. You just have to go through and calculate them. So magnesium. So we're talking about the atoms as ions. So which 2 atoms do not form isoelectronic ions? So magnesium makes magnesium 2+. We know that because it's group 2. And when it's magnesium 2+, it's going to have 10 electrons, just like neon does. Nitrogen, well, when nitrogen forms an ion, it's a nonmetal, it's going to gain electrons. So it's 3 over from the noble gases, so it makes a 3- ion, the nitride ion. This also has 10 electrons, 7 plus 3 electrons. Oxygen, same thing. Oxygen 2-, it's got 10 electrons. Beryllium. Beryllium's a group 2 metal. It's number 4 in the periodic table. So when this forms an ion, it's going to form a +2 ion. But this only has 2 electrons. So there's the one that doesn't belong. So beryllium and nitrogen do not form isoelectronic ions. All right, C. Okay. Which of the following ions is not isoelectronic with the noble gas? You can do the same thing we just did before, just count electrons. But why do these ions all form the ions they do? It's because they look like a noble gas. That's why they make these ions. Unless it's a transition metal, it's rare that you'll see an ion formed that is not isoelectronic with the noble gas. So really, you've got to look for the ion that looks weird to you. So to me, calcium plus, that doesn't exist. We know it as calcium 2+ because it's a group 2 metal. So calcium plus is not isoelectronic with noble gas. It's not missing the right number of electrons. It doesn't work.
Can I throw in something quick?
Yeah.
In case nobody else caught this. If you don't understand the ionic charge of calcium, and you're wondering if it looks, you can just take its charge, it's +1, so it lost an electron, and it then becomes potassium, and that's not a noble gas.
Yeah,
So
it looks like
even
potassium.
though it was,
Yeah, in
even
terms
though
of
it,
electrons.
if you didn't understand the electron charge, you can just run with the.
That works too, that works.
So if you got calcium, you would never use calcium plus because it would rather, like, if you pair
So,
it with chlorine. let's say.
It's complicated. So listen, if you have a calcium atom floating in a vacuum, you can definitely make calcium plus. You can strip away an electron, and that calcium ion, if floating in a vacuum somehow, will stay calcium plus.
True.
And then you can take another one away. When we talk about we never see these ions in nature, it's because whenever you form an ion in nature, like calcium 2 plus, there's always a counter ion.
Right.
And calcium 2 plus in water with the counter ion is fairly stable. Calcium plus next to a bunch of other ions next to water will never be stable. It'll always either steal an extra electron somewhere else. Does that kind of make sense?
Yeah.
Okay.
Yeah.
So the stable ions are stable for a lot of reasons that we're not getting into too much. But what we're trying to impress upon you guys is that stability is linked to being like a noble gas. Yeah.
True, because the core charge is 8. So.
Yeah. So don't confuse causation with correlation. So like there's more to it that makes it stable, but it
Yeah.
correlates with being like a noble gas. There we go.
Okay, that's okay.
Yeah. All right. The following ions are all isoelectronic with neon, which has the largest radius. So when you have isoelectronic things, you can't look at electrons anymore because the electrons are all the same, so we have to turn to protons. We're going to look at which one has, so if you want the largest atom, we want the fewest protons. The fewer protons, the less tightly the remaining electrons are held on to that nucleus. So O2 minus, it's got the fewest protons out of that group. This is going to be the biggest of these. Mg2 plus is going to be the smallest because it's got 12 protons pulling on 10 electrons, and so those shells are going to be slightly more compacted. So where's O2 minus? All right, 17 is a tough question because we've got a couple different things to look at the same time. So if you run across a question like this, group things that make sense together. And then once you've grouped things together and kind of organized them in a way that makes sense, then you can look at the two groups together. Here's what I mean. I've got fluoride, chloride, bromide, and then I've got sodium and lithium ion. And so let's do the anions first separately, and let's do the cations separately, and then let's put them together. So between fluoride, chloride, and bromide, we want to go from largest to smallest, decreasing. So the largest is going to be bromide, just because of the shells. It's got more shells. So bromide is biggest, then comes chloride, then comes fluoride. All right, let's do the sodium and lithium separately. So just based on shells, sodium is bigger. So Na first, then lithium. Now, how do we link these two together? Well, we can do isoelectronic species. We can try to see if any of them are like isoelectronic. And if you notice, fluoride and sodium are isoelectronic. They both look like neon. These two are isoelectronic. And we know how to compare isoelectronic species. So the bigger one is going to be the one with the fewest number of protons, which is fluoride. So fluoride is bigger than sodium. And there we go, we've got our order now. It's bromide, chloride, fluoride, then sodium, then lithium. So, B, yeah. That's it. Yeah, so that's a tricky one because you got to do two concepts at once. Yeah.
So for that one, would you recommend finding the elements that are isoelectronic first, or do what you did?
You can do the isoelectronic thing first. So I would group what you can, group things that are similar,
Yeah.
and then try to put the groupings together somehow.
Okay.
So yeah. So yeah, you can do isoelectronic first, and then you can do groups on a periodic table next. Doesn't matter. Okay. And again, you'll get a result that is conclusive, not inconclusive. You'll be like, yeah, definitely this. All right. The number of valence electrons in bromine. All right, this is super. I would say this is very easy. Valence electrons. Look at the group number. So Br is in group 7. It's got 7 valence electrons. All right. So here's some of the stuff that you need to remember from the quantum mechanical stuff. So a lot of the conceptual stuff that we went over, like what is a wave function? What is Heisenberg's uncertainty principle? So the quantum mechanical solutions to the Schrodinger wave equation, these are called wave functions. All right, that's when you plug in the different quantum numbers to the Schrodinger equation, you get these new equations, these new solutions that are called wave functions. And then from the wave functions, that's where we get orbitals, right? So the wave functions lead us to the orbitals, the way to kind of visualize what electrons are doing around a nucleus. 20, the Pauli exclusion principle. So there's the short form and the long form. The short form says that the Pauli exclusion principle says that 2 electrons in the same orbital must have opposing spin. One spin up, one spin down. That's the short form. The long form is exactly what D says. No 2 electrons in an atom can have the same set of 4 quantum numbers. So every electron in an atom must have a unique address, a unique set of quantum numbers. And that's ultimately where if they're in the same orbital, then the first 3 quantum numbers are all the same. So the last quantum number, the spin, must be different, which is why one is up and one is down. So D, that's what the Pauli exclusion principle states. Some of these are just, actually the rest of these are just wrong. 2 electrons in an atom can have the same spin. No, you can have them at the same spin but different orbitals. No 2 electrons in an atom can occupy the same orbital. No, you can have 2. 2 electrons in the same orbital have identical values the spin quantum number. No, that's the opposite. They've got to be opposite. And 2 electrons in an atom can have the same principal quantum number. Well, that's true, but that's not what the Pauli exclusion principle states. So E is actually a true statement. It's just not related to the exclusion principle. Okay. So this is identifying an element from its electron configuration. You can use the periodic table to do this. I would ignore the inner stuff and just focus on the highest shell, 4s2, 3d10, 4p4. If you go and look at the periodic table, just follow the groups the period over. So 4p4 ends with selenium, which selenium's in group 6a. So that's the group number of selenium. That's D.
6A, I must not have understood what the A was.
So just be clear, some periodic tables just have the numbering 1 through 18 across the top.
Yeah, that's right.
Some of them have, and honestly it's the old system. The old system is the Roman numeral with the A and the B. I think it's called the Cass numbering. But we like the old system because you can look at that and get the valence electrons pretty easily. Group 6A is 6 valence electrons.
Right.
But that is technically the old way of doing it. So a lot of periodic tables don't have that anymore. They just have 1 through 18. Okay. What is the correct condensed electron configuration for titanium? So titanium, number 22. We start with the noble gas that comes right before it. That's the argon. And then the 4s2 comes next. and then we get to the D block, we drop down a shell, 3D, and if you count over to titanium, it's 1, 2 over 2. 3D2. That's it. And it is, they're asking for condensed, so make sure you give the condensed one. None of the answers are correct, by the way, except for E, so it's fine. Okay.
How many questions are on the test, by the way?
I don't remember at all. I don't remember. It's going to be like this. I mean, there's going to be a good number of multiple choice and then a few pages of short answer. That's it.
Fair enough.
All right. What is the correct condensed electron configuration for P3+? It's on the verge of being a trick question, because normally when you think of the ion form of phosphorus, you think of P3-, because it's an anion, it's a non-metal. So we're doing not 3-, we're doing 3+, just to be clear. And so 3+ means you're losing 2 electrons. So one thing we can do is we'll do regular phosphorus. All right, regular phosphorus is a neon core, noble gas-like. And then after neon comes 3s2, 3p3. So as soon as you make phosphorus 3+, you're removing 3 electrons, and so your phosphorus electron configuration now is going to become neon 3s2. So you've lost these 3 electrons here. So B, that's it. The trap answer is E. Don't get into E. If it's a trick question, then there's a trap answer. But yeah, it's not quite a trick question, but it's close. So electron configuration for 10 2+, SN 2+. Right. Again, I think the easiest way to do these is to do the regular electron configuration first. So 10 is in period 5. The noble gas that comes before that is krypton. Famous Superman's planet. And then 5s2. 4d10, it's all filled. So you get to the P block. And then there's 2 to get to 10. So 5p2. Now, 10 is not a transition metal. So we're going to remove electrons like normal. So when I remove 2 electrons, because it's a 10 2+, I'm just going to take the highest 2. So I'm going to take the P electrons. So krypton now is, 10 2+ is krypton 5s2 4d10. Now, I wouldn't give you this in an exam, because it's a little bit beyond what we've covered. But what if I give you 10 4+? Which 2 electrons were likely to be gone in 10 4+?
5s.
Yeah, next we'd start moving to 5s. And it starts acting like a transition metal at this point. So it's a little bit weird. And these are the 2 common ions for 10 2+ and 4+. Yeah.
You said you're not going to give us
No.
choice on exam, so you don't want us to
Not
worry
the
about
4+ thing. But
do you want us to worry about the transition middle
yes.
one?
Yes. We'll see a question like that on this soon. But this is a special case where you're ionizing a regular main group element and it's acting like a transition metal later on. Yeah, so don't worry about it. But it's kind of interesting that we can see that. Okay, so 25. This is where we get to orbital diagrams. This is kind of like an orbital diagram. It's kind of an electron configuration too. So normally with orbital diagrams, we do boxes, we do lines, and we draw the electrons in. They didn't quite do that, but they did separate the different p orbitals. So get used to seeing this. So which one of these would satisfy Hund's rule? Hund's rule states that when you have degenerate orbitals, same energy orbitals, you put 1 electron in each before you pair any up.
Yours is different than mine. Are we on 25?
Yeah.
Mine says would not. It gives a large not in there?
Oh. You know what? I think I. Oh, you know what? I might have modified that for. So I think this might be an old version, but it's. I was just being.
I can tell you that I got that this
Okay.
one doesn't satisfy it.
That's true. Well, let's answer this one, and then we can go to yours in a second. So, which electron configuration would for carbon would satisfy Hund's rule? So first, it's got to be an electron configuration for carbon, and it's got to work with Hund's rule. So carbon has 6 electrons. Only A and B show 6 electrons. The one that satisfies Hund's rule is where the 5th and 6th electron, one goes into one p orbital, another one goes into a different p orbital, instead of pairing them up. So in the way we've been doing it, it's equivalent to doing this. Here's 1s, here's 2s, 2p, 1, 2, 3, 4, 5, 6. So what's online is written differently than this. If you're following this, then the answer would be B. I think the reason I put not in there is because a lot of people were confused in the wording, and I just changed it. But if it's not, then yeah, it would be A. So whichever one you're looking at. So I'll just, for posterity, since it's this version, I'm going to circle the correct answer. Okay.
Oh, actually, one question on Hund's rule. So, in your 2p orbital there on the whiteboard,
Uh-huh.
you've got 2 up spins.
Yeah.
So, Hund's rule suggests also that you can't have 2, 1 up and 1 down, right? Or is that?
That's not what Hund's rule states, but it's a. We're not. So this is more advanced, but in general, the electrons will be pointing in the same direction, even though they're in different orbitals, because I think of the magnetic influence they have on each other.
Okay.
So both up or both down are equal options, which is why when you have an unpaired electron or multiple unpaired electrons, the magnetic moment is double in one direction or double in the other direction, never cancel each other out. It's like, so you're not going to have one up and one down in separate orbitals because they influence each other. So I think that's how it works.
Right.
That's again, that's like third year chemistry discussion. So.
To be fair, it's
That takes
interesting.
more time and work.
So, which atom has the largest number of unpaired electrons? So this is again being able to do electron configurations as orbital diagrams, so you know what the spins are looking like. Pay attention to the number of electrons involved. This is plain carbon. If I'm dealing with C4 minus, that's 4 extra electrons. So 1, 2, 3, 4. Everything's paired up. So 0 unpaired electrons. The correct answer for this one, I'm just going to give it away, is nitrogen. Because nitrogen has 7 electrons in it. 1, 2, 3, 4, 5, 6, 7. So in the 2p orbital, they're all unpaired. So 3 unpaired electrons. Boron, I think, has 1 unpaired electron. And oxygen, 2 minus, and lithium plus have no unpaired electrons. So it's nitrogen. 27, this is another nice one.
This one's kind of hard.
Okay. Which set of quantum numbers is allowed? So my recommendation is to go through each step. So if energy level, first of all, is energy level 4 a real energy level? Yeah, it's 1 through infinity. So 4 is one of them. So N4 is fine. But let's look at what L's are allowed when N is 4. So the rules for L is 0 to N minus 1. N minus 1 is 3. So 0, 1, 2, and 3. Those are the allowed L's. They're all good except for this one. That's no good. You can't have a -2. So I'll cross that one out. Well. Okay, so next, we can do M sub L. We've got a couple different L's to choose from, so let's cut out a few extra. What are the values for M sub S? Regardless of the orbitals, +1/2, -1/2. This is the spin quantum number for electrons. So we skipped M sub L. We'll do that next. But these are the only allowed values for M sub S. So you can see there's a couple up there that are no good. That's no good. And then that's no good. You can't have one, you can't have two. So we're down to B and D, and that's it. So if you look at B, B has L is equal to 2. Well, if L is 2, M sub L can be 2, 1, 0, -1, -2. 3 is not one of those options. So that's no good. Alright, and it's a lot of chicken scratch here, but the only answer left is D. Yes?
If, like, everything else is right, and it's just the difference is like 1/2 or -1/2, how do you know it's 1/2 or negative?
It doesn't matter. It's so, it's one of the other or the other. They're both allowed, let's put it that way. So when you have, and I erased everything already, but you know, when you have one of these orbital diagrams, so this is carbon again. You know, and so here's carbon, 2. And if I were to ask, hey, what are the quantum numbers for this electron here? Then it's the spin down one, so it's M sub S is -1/2. But if I ask you for that electron, it's the +1/2 one. The other quantum numbers, N is going to be 2, L is going to be 0, because it's an S orbital. And the only M sub L there's just one of them, so it's 0. If it was that electron, then N is 2, L is 1. M sub L for this electron would be, we don't know which one it is. It's either 1, 0, or -1. But as long as it's one of those, it's okay. Does that kind of make sense? So the M sub L is the only one we don't know exactly sometimes which one it is. Okay. Are you cleared up on that
Oh,
question?
yeah,
Okay.
yeah.
So M28. Which of the following quantum numbers is used to describe the subshell? So this is what quantum numbers mean. N is the shell, the size. L is the subshell. All right. It's the shape. It's the subshell. So it's L in this case. M sub L is the orientation. It's the specific, it's the specific orbital of that subshell. So which p orbital is it? And then M sub S is nothing to do with orbitals. M sub S is just for the electron, the spin of the electron. Yes?
If you're gonna ask questions about the orientation, will you have diagrams of the lobes, or are we expected to draw the lobes?
I'm trying to envision like how I could ask a question. You're not going to have to draw much of anything. What you should know is that
The orientations of
what's
each
more
one?
important about, like, instead of orientation, although that's kind of what it means, the M sub L tells you the number of orbitals there are. That's kind of what's more important for us to know.
Okay.
So there's M sub L for P, there's 3 different orientations,
Mhm.
but there's 3 P orbitals. That's kind of what, but a more important thing.
So for L, let's say N equals 4, right? L is 0, 1, 2, and 3.
Yeah,
And N
0,
sub
1,
L.
2, 3, yeah.
Or actually, let's say that, L equals 2. There's 5 different orientations we could do. Do we need to know which number corresponds to which orientation?
No, no.
Okay.
That's what's unknown. Yeah, we're not at that level. Yeah.
So we don't have to know like d sub.
We don't have to know the
squared minus
dxy,
y squared.
dyz, dx squared minus y
Yeah,
squared.
yeah.
Those are weird labels. Don't worry about them. in general, you should know that d orbitals have 4 lobes, except for the donutty one. And then that's it. Yeah. Which set of quantum numbers could be used to describe a 2p electron? So 2, n is equal to 2. P is L is 1. So the only ones that fit, just A, yeah. Nothing else fits. 2 and 1, that's it. So it didn't have to be m sub L 0, it could have been 1, it could be minus 1. It didn't have to be m sub S minus a half, it could be plus 1 half. But 2, this had to be 2, this had to be 1 to be a 2p electron. Okay. What's the maximum number of electrons that can be accommodated in the subshell for which n is 3 and L is 2? You know what? Hold on a second. Am I testing? Okay, it does work. I was worried I wasn't recording. All right. So you know, n is 3, L is 2. L2 is d orbitals. So how many total electrons can you have in a set of d orbitals? 10, yeah, we can figure it out from the d block of the periodic table. There's 10 groups. We also know there's 5 d orbitals per subshell, and each holds 2 electrons, so 10 electrons. F orbitals hold how many electrons? 14, yeah. All right, you guys are experts. Gonna ace this exam, right? All right, so confident. All right. So here's identifying an orbital. So what you're seeing on the right is a p orbital. We know that because of that general dumbbell shape, the 2 lobes. Also the single nodal plane. So p orbitals have 1 nodal plane that cuts them in the middle. You know, that cuts them in a place where there's 0 electron density. So it's a p orbital. So it has to be L is equal to 1. That's the only requirement. L is 1. So A and C fit. Then we just need to make sure that the quantum numbers make sense. So 2 is 1 is fine. 2 and 1. But m sub L cannot be a minus 3. If your L is 1, I didn't write that one out. If your L is 1, m sub L is 1, 0, and minus 1, and that's it. So only A works. For some reason, 32 throws a lot of people off. So which of this is the following is largest? And they kind of get thrown off because they're like, I've never seen a metal with a -2 charge on it. Is that imaginary and that's we can ignore it? No, you have to consider all of them. So let's ignore it for a second. If we were looking at the difference between lead and lead 2+, I think it's pretty clear that one of them is going to be bigger, one of them is going to be smaller. They have the same number of protons. The only difference between them is this has fewer electrons. So remember, if there's no other kind of way to compare them, fewer electrons means fewer electron-electron repulsion, or less electron-electron repulsion. And so if there's less electron-electron repulsion, those electrons can be more tightly held on, they can be closer to the nucleus. This is definitely smaller. All right, so less electron-electron repulsion.
And that means that it's tightly held tight.
So electrons, think of them as, you know, like bumping each other further away from the nucleus. So if there's fewer electrons, there's going to be less of that noise, and so they can be a little bit closer together, closer to the nucleus. So lead is bigger, but now let's throw in one extra. Now we've got this lead 2-. And you can verify, but if you add 2 electrons, the only thing it's doing is it's adding to the same shell. We're not really seeing any difference in numbers of shells. So again, what do more electrons do? Well, more electron-electron repulsion. And if that's the case, this can get bigger than regular lead. And that's it. It's just the electron-electron repulsion. So Pb2 minus, as unlikely as this is to occur in nature, would be a bigger species. Yeah, we didn't do the electron configuration, but it doesn't change the electron configuration drastically. It just kind of subtracts and adds to that valence shell, and that's it. Okay. We got a little bit left. Oh, we got the right answer, short answer now. Okay. So we have the hydrogen atom contains only one electron, but there are many lines in its emission spectrum. How does the Bohr model of the atom explain this? So I would be looking for some key phrases here. One is, well, the main one is that it's the transitions of an electron between the energy levels that cause the lines. All right, you can't just say that the energy levels cause the lines. That's not the case. It's the transitions. So, and specifically the transitions from a high energy level to a low energy level. The other way causes absorptions. So something about transition of an electron from high energy level to low energy level is what causes all of the emission lines to show up. Okay? Okay. I'll let you guys word that yourself. One of those lines has a photon energy of 4.087 times 10 to the minus 19. What is the wavelength? So you are given some equations on the front page. We want one that has energy of a photon and wavelength in it. I don't actually give you that one. I give you this. Energy is equal to Planck's constant times frequency. And I also give you speed of light is wavelength times frequency. You can actually memorize what I'm going to show you next, or you can learn how to do this. So I want to isolate frequency over here, because what I'm going to do is I'll divide both sides by lambda. And then I'll have frequency is now equal to speed of light over lambda. And I'm going to plug this in place of frequency, because that equals frequency. And you end up with energy of a photon is Planck's constant times the speed of light over wavelength. That's the equation we want to solve this. So we want the wavelength, so I'm going to rearrange again, solve for a wavelength. I'll skip that, but this is how it rearranges. So it's going to be Planck's constant, 6.626 times 10 to the minus 34 joules seconds. Speed of light, 3.00 times 10 to the 8 meters per second. Over the energy of the photon, which is in joules, perfect, it'll cancel out. If it's not in joules, you'll need to convert it. 4.087 times 10 to the minus 19. Okay, so the wavelength is
4.86 times 10 to the negative 7.
what is it again, sorry?
4.86 times 10 to the negative 7.
Okay.
If I round it correctly.
Technically you're missing one sig fig, but it's okay. Well, if you use 3, this speed of light, if 3 is
I
fine.
used that.
I'm not going to nitpick on that. But yeah, they started with 4, so hopefully we used better speed of light. Anyway, it's okay. I used the wrong one too. Now, that's the wavelength. It doesn't specify any units, so we'll just leave meters. That's fine. But we want to know what color it is. So if you go over here, we've got our spectrum. This is in nanometers. There it is. So let's convert this to nanometers real quick, so we can compare. 1 of the prefix unit. What does nano mean? Nano means 10 to the minus 9. So this is 487 nanometers. That falls pretty squarely into blue to me. A little subjective, but I'm pretty sure that you would agree it's blue. There you go.
I said violet, but
Maybe. Okay, if you weren't looking at this part, yeah, that's fine. Very subjective. So, it's fine as long as you're close. All right.
Oh, I see, 400.
Yeah, you're gonna get a grayscale,
I'm
but
just gonna, then I will just.
it's okay. It's okay.
According to the chart, that should
Some
be-
people, honestly, it's fine because some people are colorblind, so I have to accept what
They're
they
like
say.
gray. It's gonna be
Well,
just like-
they have a, not black and white, but like they have other they perceive color differently, so like they don't see certain colors properly. All right, all right. Let's get back to the section we're at. We're almost at the end, I believe. Oh no, we got a little bit to go. All right. Use the concept of core charge to explain these trends. So, atomic radius for both going down and across the periodic table. So, core charge and distance. So when you go down a group, let's compare sodium to potassium. So we could use core charge, or we could use distance. I think here distance is a more appropriate explanation. You can use the shell model if you want even. So sodium is, actually let's make it easy, not potassium. Let's use lithium and sodium, so I don't have to draw as much. So lithium is +3 nucleus. It's got a first shell with 2 electrons. It's got a second shell with 1 electron. Sodium is a +11 nucleus with 1, 2 here, 1, 2, 3, 4, 5, 6, 7, 8 here. And then its valence electrons in the third shell. So just by looking at the shells, this electron is further away from the nucleus than this one is, and the further away it is, the bigger the atom is going to be. So we're talking about radius in part A. Across a period, let's do lithium and beryllium. So beryllium is going to be a +4 with 1 electron. And here, 2 here. The distance is not going to explain it because they have the same distance. So if we convert this to core charge model, lithium is going to be +1 core charge with a single electron. Beryllium is going to be a +2 core charge with 2 electrons. And now it's a little bit more clear that this odd looking electron, this electron, either one of these is being held on with a +2 core. This is being held on with a +1 core charge. And so these electrons feel the nucleus a little bit more over here. And so that shell is going to be a little bit more more tightly drawn into the nucleus. And so this is going to be smaller. This is going to be slightly bigger. So in terms of radius, you can look at the core charge to explain that. Yeah?
So this is what I wrote. As the core charge grows larger, the atomic radius decreases across the period because the attraction is greater.
Perfect. Yep. So then we can explain ionization energies almost exactly the same way. So if we look at down a group, the ionization energy of this is going to be higher because it's closer. Here it's going to be lower because it's further away. We can also look at core charge. They actually have the same core charge. So the attraction is the same, it's just further away. For ionization across a period, again, look at the core charge. These are being held on with a +2 core, same distance, and so they'll take more energy to ionize them. These are harder to remove. Yes.
So for the ionization energy, I said it increases across a period as the core charge grows larger because the core charge held a higher attraction.
Yes.
Okay.
Yeah. You could even use Coulomb's law and say, yeah, what you said is enough. That's fine. All right, 36 is a great problem. This is kind of making sure you understood everything we went over in the chemactivity assignments, because we built our shell model from data like this. So here's some fake data. It's from another universe, theoretically. And in this other universe, this is what the first 10 elements ionization energies are. So we're going to build a shell model from the fake universe ionization energy data. So let's start with how many electrons are required to fill the first shell of an atom. So ours takes 2. This one, so look, the ionization energy of an electron in an atom with 1 proton is this. In an atom with 2 protons, the ionization energy doubles, about. That makes sense, because it's a second proton. The ionization energy of the third proton, or the third electron, excuse me, for the third atom, is triple. So what that's telling me is that that third electron is staying in the first shell. It's not further away like it is ours. It's staying in that first shell. So it's feeling the entire +3 charge to the nucleus. But then the fourth electron the ionization energy drops. So this tells me we put that fourth electron in a new shell. So there are 3 electrons, space for 3 electrons in the first shell.
So by first shell, you mean the very outer shell?
What I mean is, so if we were drawing a shell model, lithium has space for 2 electrons in the first shell. In this theoretical universe, there's 3 electrons that could fit in the first shell. It's not real, but that's what this data is telling me. Okay, how many electrons are required to fill the second shell of an atom? So, same idea. We start from the second shell electron, and we look and see the ionization energy slowly climbs, and all of a sudden it drops. So it's telling me that, hey, that's second shell, that's second shell 2, second shell 3, second shell 4, second shell 5, second shell 6. But that's third shell. So there are 6 electrons that can fit into that second shell.
Where can you go?
Yeah, this is equivalent to that diagram that we saw. Do it over here. So when we were doing looking at this data originally, we saw it in table format, and then we saw it as in a graph, and it went. How did it go? It went up, and then it went down, and then it went up, and then it went down, and then it went up. That's basically what's happening here, but it's just different. This is, it's going up and down at different points. So, okay, so we're basically building a shell model for this, slowly. What is the core charge of an element whose atomic number is 6? So, how do we do core charge? Well, let's do it the old school way, which is do a shell model and then subtract, so protons minus inner electrons. So if I have an element that has 6 protons, it's going to have 6 electrons. We already know that the first shell in this universe holds 3 electrons. So let's put 3 of them here. And then there's 3 more, 6 total electrons. So in the second shell, it holds 6, but I've only got 3 left. So 1, 2, 3. That's what this atom's shell model looks like. Now to calculate a core charge, it's going to be the 6 protons minus inner electrons. These are the valence electrons. Everything else is inner electrons. There's 3 inner electrons. So it's got a core charge of +3.
I'm glad that didn't change since it's a different planet.
What do you mean, like?
Because hypothetically we're on a different planet and they have different rules for electrons, and we're just lucky that their rule for finding core charge didn't change.
Yeah.
I was just joking.
Yeah, well, it's a ridiculous idea, but it helps us understand that, like, everything we went through to get to this.
Yeah.
Anyway, how many valence electrons does element 6 have? Well, you can see it. It's got 3. I did the shell model. 3 valence electrons in that outer shell. So let's do a shell model for element 10. So element 10, I don't even have to look at it. I know it has 10 protons, 10 electrons. So it's going to have a plus 10 in the middle. And so there's 10 electrons. The first shell holds 3. The second shell holds 6. That's the max. We've figured that out already. So that's 9 total so far. 3, 4, 5, 6. And then there's one more, 10th. It's going to be the third shell. So there's the 10th electron. So that's E. That's the shell model for this element 10. Now, let's do a shell, core charge model. So showing the placement of electrons using the core charge concept. So if that's the shell model for element 10, the core charge model, well, let's calculate core charge first. It's 10 protons minus 9 inner electrons, right? The only valence electron is that one. Everything else is an inner electron. So 10 minus 9 is plus 1 core charge. So we're going to have a plus 1 core. And then that one shell 3, I'm just going to label this just to make sure. This is shell 3. This only got 1 electron in it. So there's the core charge model. Okay, so G. Which of the 10 elements would you expect to be largest, which is smallest? So we got to go back to this. So largest. Which one would it be? Probably that one, because it's got the most shells, and the size of your atom is defined by how far the electrons can go. The third shell electrons go further up. So that's our biggest. Which one's our smallest? So when we look at our periodic table, what is the smallest element?
Helium.
Right, so when you go left to right, what happens to the size?
Right.
So the further to the right you go, the smaller they get. So helium is the smallest.
Right.
So in this model, Ft is the smallest because it's the first shell, so it's row 1, period 1, but then it's furthest to the right. So that's the smallest, Ft. And is that it? Well, almost. So that's it for that. So that's an awesome question that hopefully proves you've been paying attention. But 37. When you get to this problem, make sure that they're isoelectronic. So which noble gas is each ion isoelectronic with? What I meant by that is, if you're comparing these, make sure they're isoelectronic with each other first, so you don't run into any mistakes. But Sc2 minus looks like krypton, bromide looks like krypton, rubidium plus looks like krypton, yeah, okay, and then strontium 2 plus looks like krypton. They're all isoelectronic, and they're all isoelectronic with krypton, Kr. Which one's the biggest, which one's the smallest? So if they're isoelectronic, we go by numbers of protons. Sc2 minus, which has the fewest protons, is going to be the biggest. So Sc2 minus is the biggest. That's next. That's next. That's the smallest. That's SR2 plus. Okay. Oh my God, I went too fast. Oh, we have lots to do. Okay. I thought that was the last page. So, photoelectron spectroscopy. So, we have this. What is the electron configuration for this this diagram, this spectrum? Well, you can literally write electron configuration directly from the peaks. The highest energy one, assuming they show you all the peaks, but the highest energy peak is always the innermost one, the 1s. And if that's full, it's going to be full because we've got electrons way up here too. That's always 2. So this height represents 2 electrons. All right, after 1s comes 2s, and that's full too. After 2s, next is 2p. There's the tall 2p peak at 29. That is full as well. It's got 6 electrons. You can say if this represents 2, there's 2, 4, 6 electrons. After 2p is the 3s. That's full. After 3s is the 3p. That's the same height as the 2p, so that's full as well. After 3p, there's another peak, is not 3d. After 3p comes 4s. Remember your ordering. Go by the periodic table if you need to. And there's only one electron in there, because this peak is half the height of these. So that, the small peaks, these small peaks represent 2, that represents 1 over there. That's it. That's the electron configuration. So this is fantastic. Yeah. Okay. All right. They look so daunting when you guys started it. They're not that bad. Electron orbital diagram. Well, basically you're just writing the boxes as orbitals and filling them with electrons. Anything that's degenerate, connect it. And I'm running out of room here, so 4s is down here, even though it should be in line. This is all full. This is all full, full, and then 1 electron. So D is, you know, the only distinction, the difference between C and D is exactly like C, you're just showing it on an energy level diagram, that's it. So instead of just writing it horizontally like this, you're going to put your little energy arrow and then start from the bottom. And you can use boxes if you want. I like the little lines. Just do that. And you don't have to put anything sideways. You could put them all on top of each other. Doesn't matter. But it looks a little cleaner like this. And that's it. And then fill it up. That's the only difference.
So that's the energy diagram, and the orbital diagram is that one to the right there?
I mean, they're both orbital diagrams, but this one shows the energy as well.
Okay.
So, yeah, electron energy. So this doesn't show the energies. This just shows the order. That's it.
True, but I could put an arrow at the top that had an E pointing to the right. Would that not be the same?
Well, theoretically, and I'm just guessing where they belong on the line, but theoretically these would be at the right spots. Like they would have like actual energy markings.
Okay.
But I don't know what they are, so we're just guessing here.
Fair
Yeah, that's the only difference. It's not a big difference. And here's the last one. We're ending really early. The electron configuration for nickel 2+. So this one is a little unique in that nickel is a transition metal. So we went over this last week. I think it was the last thing we did. So let's do plain nickel first. So nickel is an argon core, 4s2, and then 3d8, I think. Yeah.
It says full electron configuration, so can we do
Oh,
that again?
yeah, sorry. Let's do the full one.
No cheating.
God, you would have got this wrong, Lee.
Oh, yeah. I don't read my own things. All right. 1s2, 2s2. This is for nickel. 2p6, 3s2, 3p6, 4s2, 3d8. I didn't need that much room. There we go. So when you turn this into nickel plus, the only difference is, since this is a transition metal, we're not going to automatically take from the highest energy subshell. We're going to take from the 4s instead. So these are the electrons that go first, and so this is going to be like that. That's only for transition metals. Notice that when we did 10, we didn't do that. We took the p electrons first, because 10 is not a transition metal. Alright. That's it. You guys are like, this is no problem, right? Or at least you need a little bit of studying and then it'll be no problem. Questions, please, yeah.
So, my question is, the information that wasn't covered in this, like the stuff we're gonna need to know from the Schroeder, or I don't know their exact names, the equations. You said we needed to know, that Y symbol,
Oh, the wave function.
the wave function,
Yeah.
is it just being able to define
Yeah, you
what
don't-
the wave function is,
Yeah,
or?
you just need the concepts, that's it. You don't, that equation that I showed you don't have to worry about that. The Schrodinger wave equation, don't worry about it, just know what it does for us, that's all.
What does,
So the Schrodinger wave equation is an equation that lets us, if we solve it, and you have to plug in a bunch of parameters, that includes the number of protons, all that stuff, and the quantum numbers, we can solve we'll get wave functions out of it. So more equations. And what these equations, these wave functions do is they let us, ultimately let us figure out orbitals. They give us the positions where we're most likely to find electrons, and they give us their energies. The other main thing out of that chapter is to understand, besides the quantum number stuff, is to understand that these positions of electrons and the energies of the electrons are not going to be precise anymore. Heisenberg's uncertainty principle says that you can know either one of them with great certainty and then the other without any certainty, or you can have a little bit of uncertainty for both. So it's just a consequence of treating electrons like a wave now instead of like a particle. We have to talk in probabilities now. So when it comes to if the electron is located here, we can't say that anymore. We can say the electron has a such and such chance of being found here. So that's kind of what Heisenberg's uncertainty principle are. Those are the results of Heisenberg's uncertainty principle.
And that's position and energy?
Yes. Technically position and momentum, but you can think of momentum like energy, yes.
Well, we need to know how to like, I don't know, make the photo of the spectrum.
Oh, how to draw one?
Yeah.
Kind of. I mean, you should be able to look at any atom on here and draw an electron, write an electron configuration for it. And if you can write the electron configuration, you can kind of come up with a photoelectron spectrum, because all you're doing is you're going to write, like for nickel, you would do a small peak because it's 2 electrons in the beginning, and then you do a small peak right after, and then you do a 3 times the height peak, and then another small peak, and then another 3 times the height peak, small peak, and then this one's going to be 4 times the height. So in that order, like you have to remember that there's going to be a big gap between the shells for energies, but for subshells they'll be close. So going back to what I mean by that is, so notice that this is shell 1. There's a big gap between shell 1 and shell 2. Here's shell 2, and there's a big gap between shell 2 and shell 3. And 4 is close to those, but you know, you don't have to know where these energies are, like the actual, these numbers. You don't have to do that at all. It's just, but ultimately you should be able to come up with a pattern. Yeah. Yeah.
So when we're using D, like 3D,
Uh-huh.
let's say this one had 3D, we wouldn't put that with 3, we'd put that with 4, like with our dash marks.
So if we were doing nickel, plain nickel, the way this would look is everything would be shifted over a tiny bit. This, the 4s, would be twice as high, and it would be shifted over, and then the 3D would actually come lowest in it.
Oh, okay.
And it would be 4 times as high,
Oh, okay.
because there's 8 electrons in it.
Yeah.
But yeah, that since the way we write our diagram, our energies, at least up to here, this is correct. This is the highest energy.
Yeah.
Or, yeah, highest, closest to 0.
Yeah, okay,
So lowest ionization energy.
okay.
Oh, that's a good question, actually.
Okay.
Dude, you could ask that.
Well, will you ask a question where we have to draw the put electrons vector?
It's possible. Yeah, somebody was just, yeah, she was asking that, yeah.
Oh, sorry.
That's fine.
So 3D8 is the lowest ionization energy.
Yes.
Is
It is the highest potential energy, so it's closer to 0, so it's the lowest ionization energy. And I'm pretty sure that's why the axis here is backwards, because this is actually deeper inside the molecule, and it makes sense to think of that as further to the left for us, but that's probably why they did that. Okay. Anything else? We can go, and if you want to stick around and do 101, we can do that too. It's up to you.